Hello. I'd like to talk about binary constraint trees and structured decomposability. So first, I would like to introduce the notion of binary constraint trees. Then I would like to talk about structured decomposable negation normal forms. Then I would like to state the main result, which is the equivalence up to a polynomial vector between these two types of representations. And then I would like to briefly give an idea on how we can translate a binary constraint tree into an SDNNF, and then the opposite direction. And then I would like to conclude the talk. So we will be talking about representation of constraints. So I would like to first introduce the basic notation I will use. So a CSP to us is a pair of a set of variables X and a set of constraints C, where each variable has a finite domain. And we also say that if we look at a pair of a variable and a value from its domain, that it's a literal on the variable X. So it's a slight generalization of propositional literal. A set of literals is then a tuple. Usually we also assume that the variables inside the tuple are pairwise different. Each constraint is defined by its scope and a relation. A scope is a set of variables on which the constraint C is defined. And the relation of C is the set of tuples that satisfy the constraint. And they are the tuples on all the variables from the scope. So if you are looking at CSP P, then a solution of P is a tuple tau over the variables X that satisfies all constraints in the set C. So P here is the pair X and C. In particular, restriction of the tuple tau to the scope of every constraint C belongs to the relation of C. Okay, so given that there are various ways how we can represent constraints, and one of them was introduced by Wang and Yap in the 2022 paper. And the idea is that we can use CSPs to constraint to represent much more complex constraints or other constraints. And in particular, it's useful to use normalized binary CSPs whose constraint graphs are trees. And we call these binary constraint trees. So for example, in this picture, if we consider that the domains of all, that we have 4 variables with domains 0, 1, and 2, and 3 relations between the pairs x1 and y, x2 and y, and x3 and y. Each of these relations states that the respective variable xi is not equal to the variable y. Then we have a CSP on 4 variables. This is a binary constraint tree. And the idea is that we can use these to represent other constraints in the following way. So if we have a binary constraint tree P that is defined on the variables Z and constraint C, then we can use it to represent a constraint on variables X. These are called original variables. But in addition to these, we also use some hidden variables that are in the Z minus X. If we use it to represent a constraint, which is then called BCT constraint. Then the constraint relation is given by the solutions to the binary CSP P that are restricted to the original variables X. So we sort of use the hidden variables only for the representation purposes. They are existentially quantified. So this is very common in, say, when we are encoding problems into satisfiability, that we use existentially quantified auxiliary variables. So, for example, if we go back to the example of a binary constraint tree on the variables y, xy, x1, x2, and x3, we may consider y as a hidden variable, then x1, x2, and x3 would be the original variables. And if all the domains are 0, 1, and 2, then we get a representation of a BCT constraint that states that x1 is equal to x2, or x1 is equal to x3, or x2 is equal to x3. So this is a negation of an all different constraint on these three variables. So if because if we would have that, for example, x1 takes value 0, x2 takes value 1, and x3 takes value 2, so all these would have different values, then we don't have any value to spare to be used to be assigned to variable y. So the BCT constraints have very nice properties with respect to consistency checking and propagation. So in particular, consistency checking and propagation can be done efficiently. This is actually known for quite some time, because it's known that the consistency of BC binary constraint trees, or in more detail, CSPs with tree structure, can be checked in polynomial time. It was also shown in the paper by Wang and Yap, in some of the papers actually, that multivariate decision diagrams can be encoded as BCTs. Constraints that can be represented with non-deterministic finite automata can be encoded as BCTs. BCTs admit propagation complete encodings, and there are some results also with respect to combinations and query answering in the newest paper by Wang and Yap. So in particular, we can efficiently combine several BCT constraints that have the same tree structure into a richer constraint, like take their conjunction or disjunction. So our result is that actually BCT constraints are polynomial equivalent to another structure or another representational language that is commonly used in knowledge compilation, and that's the language of structured DNNFs. So let's start with negation normal forms. So in the multivariate negation normal form is a circuit in which the inner nodes, or directed acyclic graph that represents this circuit, the root node represents the output of the circuit. The leaves corresponds to the inputs to the circuit, and as the inner nodes represent gates, these are either conjunctions or disjunctions, and the inputs or the leaves of the negation normal, this multivariate negation normal forms, are associated with literals. But unlike in Boolean case, here we consider the multivariate literals, which means the pairs of a variable and a value from its domain. So if we would identify x1 with x1 0 with negation of x1 and x1 1 with x1, we would get the negation normal form as a representation of Boolean functions. So we may consider these as a representation of constraints as well. So a negation normal form constraint C is represented with a negation normal form D, where the scope is given by the variables in the leaves, and the relation is given by the tuples on which the circuit D would evaluate to true. So in particular, so if you have a tuple tau, then we set the littles in tau to true and the littles that are not in tau to false, and then we use the usual rules for evaluating the monotone circuit with conjunction disjunctions to propagate the value to the root. So there are the two most important subclasses of negation normal forms that are like most important for our result are the decomposable negation normal forms, in which we require that every conjunction gate is decomposable. These were introduced by Anand Darwich in 1999. They allow efficient consistency checking and efficient propagation. There's a propagator described by Gang and Stuckey from 2012. And then these were further restricted to obtain structured DNNFs, where the conjunctions are moreover required to have a tree-like structure. These were introduced by Sisawat and Darwich in 2008, and they allow an efficient conjoining of two structured DNNFs with the same structure. So that was the reason why these were introduced as a restriction of, or as a special case of decomposable negation normal forms. So let's start with decomposable negation normal forms. So we say that a conjunction gate is decomposable if the inputs to the gate depend on pairwise disjoint sets of variables. So for example, if you look at the top, so in here, each gate is accompanied with or annotated with a set of variables that are reachable from the gate, so from the inner node by a path, and these are the ones on which the inner node depends. So for example, in this case, here the left, bottom left conjunction gate depends on x1 and x2. The same goes for the bottom right, that depends also on x1 and x2. And their inputs, the left one always depends only on x1 and the right one only on x2. And in the top row, the conjunction gates depend on the three variables x1, x2, x3. And again, the left inputs depend on x3 and the right inputs on the rest of the variables. So the sets of the variables of the inputs associated with the inputs are disjoint. Now, the structured DNNFs are defined based on a V-tree. A V-tree is simply a rooted binary tree where the leaves are identified with variables. So it's like this one. And then once we have this tree, we can say when a conjunction gate respects a particular node in this V-tree. So in this case, we say that A, the node A, the conjunction gate A, respects T, which is the node of a V-tree, some particular node of some particular V-tree. If the following condition holds, that the left inputs to the gate A, which is this AL, depend only on the variables that are below TL. So not necessarily all of them, but all the variables that are below AL are also below TL. And the same goes for the right input. So AR is all the variables that are below AR are also below TR in the V-tree. So for example, we go back to this circuit. The top row nodes, conjunction gates, respect the V-tree node T0, because we always have that the left input is x3 and the right input depend on x1, x2. And the bottom row of conjunction gates respects the node T1. So this is a structured DNNF because every conjunction gate respects some node of this particular V3. So structured DNNFs have, again, very nice properties. They were introduced in 2008, as I mentioned. They include structured decision diagrams, which are all the well-known diagrams like ordered binary diagrams, multivariate decision diagrams, sentential decision diagrams. They are strictly less succinct than DNNFs, which means that there are some functions that can be represented with a small DNNF, but not with a small structured DNNFs. It might be also of interest that they are strictly more succinct than on the other hand than A and or MDDs. And because they have this structure, they also allow, for example, efficient conjoining of two SDNNFs respecting the same V3. Okay, so our result is that PCT constraints are polynomially equivalent to structured DNNF constraints, which means two things, so that the PCT constraint can be transformed into an equivalent SDNNF, and SDNNF can be, that represents some constraint, can be transformed into a BCT encoding of these constraints. So now I would like to give an idea of how to translate a binary constraint tree into a structured DNNFs. So the idea is that, so first of all, so in a BCT constraint, we have this tree structure, but this tree structure is not rooted, and it is not directed. On the other hand, in SDNNFs here, we must have also a tree structure, but this tree structure is inherently directed and rooted because we go down the circuit. So the first step is that we will pick one node from the T structure of the given BCT constraint as the root and direct all the edges away from the root. Then we will proceed from the leaves to the root, and for every variable and Z and every variable A in its domain, we will construct an SDNNF that represents the constraints below Z, assuming that moreover that Z takes value A. So this is done in the following way. If Z is actually, so if Z is a leaf in the tree, then the DNNF is simply a single node that represents the literal ZA. If Z is an inner node in the tree, then we combine this SDNFs that for the constraints that are leaving the variable Z in this tree. Then we will this way we will construct the DNNF DP for the root, which will be a combination of SDNFs for the constraints leaving the root. And as a last step, we have to forget the hidden variables in DP to obtain DNNF T that represents the constraint C star. So let's see this on an example. So we will consider the following BCT that has four variables. X1, X2, and X3 are the original variables. Y is a hidden variable, and the constraint represented by this binary constraint 3 is a constraint that represents that the maximum of X1 and X2 is strictly smaller than X3. The domains of all variables are 0, 1, and 2. So first step is to pick at the root. So we will pick X3 as the root and direct all the edges away from the root. Then we construct SDNNS for the leaves, in this case for X1 and X2. And on the way, we are also constructing the V3s. Right, so it's easy because, for example, the X11 is the DNN that represents just the fact that X1 takes value 1. It's defined only on variable X1 because nothing is below X1. For X2, it's the same for all the values. Now we consider the little y0, for example. So y, if you go back, y is in the middle. So we have two constraints below y, leaving y, c1 and c2. So we have to take them into account. And the idea is that if y is 0, then we put a conjunction to the root where one of the input states that y has to take value 0. So this way we are kind of restricting the values to y having value 0. On the right-hand side, we have a conjunction where we say that both constraints, C1 and C2, must be satisfied. And for each of these constraints, we have a disjunction, which in this case is trivial. Because if y is 0, then to satisfy constraint C1, we have only one choice, to have x1 being 0. And for C2, also x2 must be 0. So that's why this is very simple. The disjunction is actually has just one input. It's maybe more interesting. So actually, yeah. So and we also have the V3, which is constructed on the way, follows the structure of the DNN. Okay, so it's maybe more interesting to look at a situation where y can be a value 1. So if y has value 1, then again, one of the inputs to the root conjunction gate is states this fact. And then on the right-hand side, we have a conjunction of two subtrees that represents the fact that C1 is and anything that is below C1 is satisfied, and that anything below C2 is satisfied on the right-hand side. So if C1 should be satisfied, then the C1 states that x1 is at most y, and therefore if y is 1, then x1 is either 0 or 1. So we take a disjunction of these two DNNFs. And the same goes for the right-hand side. That's the same constraint, only with x2. Yeah, and we also have the same V3. That's the same as for y0. So the V3 doesn't change. It's still the same no matter which value we consider for the particular variable. Okay, so for y2, it's the same picture, only slightly more complicated, because if y is 0, then we also have to consider that x1 can be 0 and x2 can be 0. We get the same V3. And we would continue this way. We would obtain this final picture and the V3 that has 3 inner nodes, and the leaves are labeled with x3, y, x1, x2. So the root here represents the whole structure. So the root basically says that it's a disjunction over all values in the domain of x3, and for each of them it states the subcircuit represents the fact that if x3 takes value 1, then we can satisfy the constraints that are below the root, which are all the constraints. So that's why the top node, the root here, is a disjunction. So now we can see that so this is almost now we are almost done, but we still have this hidden variable y. But in a negation normal form constraint, we don't allow hidden variables. We just have the variables. All the structure, in BCT constraints, we use hidden variables to have some inner structure. In case of negation normal forms, we have inner structure defined by the gates. So we have to forget y, which means simply removing y. In general, in a DNNF, and as DNNFs as well, forgetting means satisfying all the leaves that represents the literals on a given variable. So in this case, it would be setting y2 y0 and y1 to 1 to true. But because they are inputs to a conjunction, it's the same as just removing them. Then we have then we can actually simplify the circuit, because there are some gates like this dy1 and some others that have just one input, and these can be removed trivially. So by simplification, we get the picture we started with. We still have the same V3. Well, so the V3 is obtain also by forgetting the variable from the original VT. Okay, so this was the direction when we start with a BCT constraint and we construct a structure D and an F. Now I would like to give just a short idea on the opposite direction. So if we are given a structure D and an F, D that represents constraint C star with scope X and a V3T, then we want to construct a BCT P defined on variables Z and C that encodes this constraint C star. The structure of P will be actually equal to T. The variables Z will be the original variables X, and then we will use as hidden variables. The hidden variables are defined as follows. Basically, for each inner node T of the V3T has an associated hidden variable YT. The domain of this hidden variable consists of the conjunction gates with so-called D node T. So now let's look at what is the D node. So D node is the deepest node that is respected by of the V3 that is respected by the node B, the conjunction gate V. So for example, in this case, the top row conjunctions have a D node T0 because there is no deeper node that would be respected by these two. And the bottom row conjunction are respected only by respect only T1, so that's also the deepest node and the D node. And the idea is that now if you look at this picture, then it's useful to look at this is in terms of certificates. So basically, if this circuit should evaluate to true, then we have some gates that evaluate to true. In particular, the root must evaluate to true. Then there are some gates that do not evaluate to true with a given assignment. And from the satisfied gates, we can take like a minimum or a minimal sub circuit that still is satisfying, but we remove the gates that are not needed to witness this fact. In this way, we obtain a tree. This is the result, or this is the reason. This is because the structure, the DNF is decomposable. So this is due to decomposability. Now, this tree is called a certificate. So it's also a minimal satisfied subtree. In particular, we can show that assuming some further technical assumption of smoothness, that for every node T of the V3, S contains exactly one conjunction gate with D node T, if the DNF is structured. So we will set the relation of the constraint that connects T with T prime, where T and T prime are the nodes of T. So actually, every variable of the constructed CSP is a node in the V3. It's either a leaf when it's original variable, then we basically define a constraint with a scope where V and XA, where V is a conjunction gate with D node T, or the tuple that represents that's part of the relation are the one part is the conjunction gate with the D node T, because that's one side. And if T prime is a variable, it's a leaf, then we consider the values XA for this particular conjunction gate that are reachable from V only by using conjunction gates. And for inner node, it's very similar. Only on both sides we have conjunction gates, and the values are these conjunction gates. So maybe it's best to visualize this on an example. So in this case, the V3 now changed into the tree of the binary constraint tree. Now, why T0 corresponds to the inner node T0? and it's connected by a constraint to X3. So basically here, if a conjunction gate A should be satisfied, then X3 must be satisfied. It must take value 1. If B is satisfied, then X3 must take value 2. The same goes for YT1 and well, not the same, but similarly, we can proceed between the other constraints. So for example, if between YT0 and YT1, it's relating these two levels of conjunction gates. So if A should be satisfied, then C must be satisfied. So that's why we have this relation between A and C. If B is satisfied, then either D or C is satisfied. In both cases, we get that the disjunction gate in the middle is satisfied and B is satisfied. And then we add a similar relation between YT1 and X1 and YT1 and X2. Now, and we actually get back to a very similar picture to the original BCT we started with. Okay, so this was just an idea. To conclude this talk, so first thing I haven't mentioned is that the construction of an SDNNF from a BCT actually enforces arc consistency. So we might have actually seen that in this picture, which is the final circuit of the constructed by the construction given the initial BCT, we don't have, for example, X3 with little X3 0. And that's because X3 must be strictly bigger than both X1 and X2, therefore it cannot be 0. And this is in the process of the construction, this is detected, and these parts are not even present in the result. The size of the SDNNF can be parameterized by the domain size and the tree width of a binary CSP. The idea is that CSP can be binarized and SDNNF can be constructed for any CSP in this way. So, and we would get a construction, basically binary constraint T's can be parameterized in this parameter. An interesting application of this approach is that structured DNNFs could be sort of restructured by picking another V3 node as the root. So if you have a V3 of a structured DNNFs, then we can go to a BCT constraint, pick another root, and go back to an SDNNF. We get the same representing the same function. The V3 will be changed, but only by picking a different root. That's the topology of the tree will be still pretty much the same. So the change is not big, but still it's a slight modification. The main message from this result is that whatever is known about structured DNNFs can now be applied to binary constraint trees and vice versa. So, and there's quite a lot that is known from the knowledge compilation perspective on structured DNNFs. And there is quite a lot that is known about binary CSPs that have these structures. So these two were shown to be equivalent, so they can the results can be transferred in both directions, which can benefit both constraint programming and knowledge compilation, I believe. As a side effect, we also get that the knowledge compilers that compile into an SDNNF, like maybe from a CNF, for example, or into, say, structured decision diagram, can now be used to compile into a binary constraint tree. So, and with this, I would finish my talk. So I thank you for attention.